Okay, so I'd like to talk about computational materials design. I'm sure there's been much discussion that sustainability issues are often driven by materials processing. So we're often the cause of problems, but as well, new materials are an important part of solutions to sustainability issues. But historically, as expressed by the ongoing Materials Genome Initiative, the old way of empirical material development has been too slow and costly to meet the challenges the way we want to. But now that we have computational materials design, it can greatly compress not only the time scale of the cycle, but more importantly, the cost of the cycle. We now have a system of affordable change that puts us in a much stronger position to respond to those challenges. So that's the practice I'd like to talk about, partly from the viewpoint of my day job, which is now at MIT, as well as the ongoing activities at our company, Questech, and their collaborations under the NIST-sponsored CHIMAD Design Center supporting the Materials Genome Initiative. Historic milestone in the development of this technology was a decade ago with the first flight of landing gear made of Questech's Ferrium S53 stainless landing gear steel. This was the first stainless steel to meet the mechanical performance requirements of aircraft landing gear. And in so doing, enabled the elimination of toxic cadmium plating for the first time in these applications, where the Air Force alone in maintaining these systems was generating something like a ton a year of cadmium waste into the air and water. So this actually was a green steel design project supported by the CERDIT program, Strategic Environmental R&D Program, joint agency, DOE, EPA, and DOD that got behind that. So it's our first example of using this technology to resolve such an issue. But probably more significant is that this represents the very first fully computationally designed and qualified material to go all the way to flight. And it really measures a level of maturity of this technology already a decade ago. And that maturity is reinforced by this timeline. There continues to be some debate as to what a materials genome could be, but it's clear the genome we have is the CALIPHAD system of fundamental phase level data, whose origins can be traced back to Kaufman and Cohen in 1956 at MIT. Becoming an international organization in the 1970s and expanding beyond solution thermodynamics to molar volumes, atomic mobilities to solve dynamic problems, and even now elastic properties. Historically, all empirical measured data, deduced from phase diagrams primarily, but with the improved accuracy of DFT methods, first principles energy calculations are now a significant contributor to that overall process. It was the emergence of commercial software, starting with ThermoCalc in the 1980s, that inspired our founding in 1985 of our SRG Design Consortium to build a practice of computational materials design motivated by the existence of these genomic level databases. We focused on steel first, acknowledging that it's still the class of material we've studied the longest and deepest, not only have the highest mechanistic understanding, but the highest quality of fundamental data to support it. But from the start, we wanted to use that as an example to demonstrate a general methodology that could be applied to all materials. In the 1990s, it led to several steel designs that then led to the founding of Questech in 1997 to commercialize those steels and offer design services. But in parallel with that, at the university, we did a number of demo projects to apply the same methodology to other alloy systems, polymers, ceramics, and even some composite systems. And I think it was the successes in design of materials in the 90s that really helped to make the case for the DARPA AIM initiative starting in 2001 that is the start of what we now call ICME, or Integrated Computational Materials Engineering. And this was to go beyond the process of arriving at a material composition and process specification, and really address what is the current goals of the Materials Genome Initiative, which is to compress the full materials development cycle. That means process scale-up, process optimization at the component level, and most importantly, the quantification of manufacturing variation to specify minimum properties that can be the design allowables for a material user. And doing that the old way was 90% of the time and cost of getting a material usable. So the DARPA AIM was the first example of doing that in the, for the case, demonstrating it with the case of a aeroturbine disc nickel alloy, but we went on to apply this to steel applications since. So at this point, we've really got over 6 decades of building out the fundamental genomic database structure, more than 30 years of well-established design practice, and now really 20 years of a fully integrated process. And this has been written up in various Academy reports, and significantly, it is the 2004 Accelerating Technology Transition Academy study that really used the example of AIM to really pose the issue and call for the Materials Genome Initiative to broaden the application of this technology. And I should say, as I'll get to in a minute, I think the most important aspect of that cycle acceleration is really, for the first time now, materials can enter concurrent engineering, which historically has meant everything but materials. If it took 20 years to get a new material out, you had to go with the materials you had. We really now have this new opportunity, and there's a really very powerful synergy that enables. And the approach that we take is based on taking the well-established framework of systems engineering and putting our predictive material science mechanistic understanding within that framework. So that we start each project with this type of a system chart to represent the entire material on a page, by which we can map a performance goal to a set of quantitative property objectives that, from our knowledge of structure property relations, we can map back to the hierarchy of microstructural subsystems that we know dynamically evolve through the sequential stages of materials processing. And from this system perspective, we can identify and prioritize the structure, property, and process links for which we want to build predictive models. And I should emphasize that what the CalFAD databases are allowing us to do is, instead of settling for superficial correlations, we really can take mechanistic understanding and make it quantitative in a system-specific way. So for the first time, we can really use our scientific knowledge to engineer with. The research that this is motivated is summarized by this set of the tools that we found useful for science-based engineering. So the performance-driven design is integrated the quantum mechanical DFT methods, the material science of nanoscale precipitation strengthening, and the continuum mechanics of unit processes of fracture and fatigue. Equally important are the material science models that constrain scale-dependent process abilities, and that's the solid-solid and liquid-solid phase transformation models, which through the ICME technology, we can then link to macroscopic process models where largely scale dependence comes through heat transfer. But having that capability, it's possible then to constrain our designs up front for processability at the final scale of production and eliminate experimental scale up. So we have a number of examples now where we got it right. We can still test at a smaller scale, but we've already made the predictions of what will happen at full scale. Here's the example of the timeline and applying this technology to 2 aircraft landing gear steels designed and qualified by Questec. So the scale on the left is the technology readiness levels at the landing gear level. And then on the right are the corresponding materials development milestones. Both of these landing gear steels were able to go from a clean sheet to flight qualification in under a decade, meeting that goal of the Materials Genome Initiative. But the second one, which is our high toughness steel for carrier-based applications, it became the subject of a NIST-sponsored case study for the MGI that looked at what were the technology accelerators that enabled this, but as well, what were the inhibitors in doing this in the environment of a small business. And it was concluded that the technology demonstrated would be capable of a 3-year cycle, which really gets us down to the level enabling concurrency. And the historic example of that was the announcement of the 4 new alloys that were announced with the release of the Apple Watch in 2014. It's the first time that Apple advertised creating their own materials. These 4 alloys were created concurrently with the design of the device and delivered in less than 2 years from acquiring the technology that enabled it. And the anodizable 7000 aluminum alloy made its way into the 6S iPhone and on, so that it has since been estimated there's now a 50% chance that you have a computationally designed material in your pocket. All of this caught the attention of this man, and it became public about 5 years ago that my former student and founding Questech CEO, Charlie Kuhlman, left Apple after 3 years there to join both SpaceX and Tesla as the vice president of materials engineering. And so this technology has had a tremendous impact on both of those companies. And this led to a rare example of an American corporate CEO bragging about his metallurgy. This doesn't happen very often, but this is heralding the burn-resistant nickel superalloy that is really the central enabler of the concept of the Raptor engine for the Mars Starship. So this was really a very important material advance that was central to the design of that engine. And in fact, the initial design was done at Questech. But in fact, this has gone into a very high level of concurrent engineering where an essential nascent material was integrated to the actual building and testing of these engines in a way that never would have been done before. And what's enabling it is the inherent predictability of a designed material as opposed to a discovered material. So it really is a brave new world of concurrent engineering that's going on at SpaceX. Interestingly as well, Charlie's got 2 groups of 30 people at the 2 companies practicing this technology with a very strong synergy between the groups. And I think something that's very new is we're seeing development of automotive materials at the same pace that they're developing their aerospace materials through the synergy between those 2 enterprises. And in the arena of automotive lightweighting, it's Mr. Musk's dream to make an affordable aluminum lightweight car in 2 die-cast parts. And they've actually designed the new die-casting aluminum alloys and the plant in less than 2 years to do that. The last I heard, they were doing 1/8 panels on their way to 1/4 panels. So they really are going to create another materials-enabled radical manufacturing technology for affordable lightweight structures. So it's quite amazing to see the level of concurrency that this technology is now enabling and the kind of issues that it's responding to. About a decade ago, I had occasion to read thousands of pages of DOE reports that were saying that the best opportunity to reduce our energy losses and unnecessary emissions in primary power production was to burn fossil fuel hotter. Interestingly, over that decade, the biggest expansion in power generation globally has been the building of new coal plants, which sounds pretty bad. But in fact, I heard a presentation in Stockholm year before last that in fact, with those new plants, they are using new steels that can run hotter. And they've actually allowed the new plants to move from 40% efficiency to 50% efficiency. So that is this very substantial increment in associated reduction of carbon emissions, which may well have been the largest global impact on reduced carbon emissions. So back in the US, we love our shale and want to keep fracking it. And so the opportunity for us is natural gas. A problem that was called to our attention by Howmet in the late 90s is the incompatibility of the highest performance aeroturbine blade alloys with the scale of industrial gas turbines, that the rhenium-bearing alloys cannot be produced at larger scales because of a thermosolute convective instability during solidification that causes freckle defects. And we looked at this with Howmet at that time in the late 90s. All the physics is known. The issue was at that time there wasn't enough accuracy in the available CalFAD databases to really address the problem. So fortunately, within the last 5 years, we got the opportunity at Questec under DOE support to return to this problem, and using some new uncertainty management strategies for CalFAD-based design that came out of the DARPA AIM program and some follow-on programs. And so we were able to down select the best available database for each attribute that we needed to control, and succeeded in delivering a 1 rhenium alloy with the processability of a rhenium-free alloy, which meant it could go all the way to IGT scale. And then exploiting multi-component thermodynamics, we were able to partition the rhenium more efficiently and get the creep performance of a 3 rhenium alloy. And so this has been demonstrated at scale already by Siemens and is moving into the application. And so this will be a significant improvement in the efficiency of IGT. We are just now starting a new ARPA-E program in collaboration with Pratt & Whitney. And through the technology of 3D printing, we are looking at multi-alloy refractory metal-based printable alloys to make turbine blades operate at 1300 C, with the ultimate goal of taking that to the IGT technology. And that would be a very substantial boost in efficiency. What I wanted to say going forward, under MGI 1.0, our CHIMAD Center has built out a well-established full methodology from design to qualification, but also built out an infrastructure of the database hierarchy shown in yellow here, which means not only the fully assessed CalFAD data, but a repository for pre-CalFAD raw data. And at that level, high throughput DFT has been very effective. I would suggest that the opportunity going forward in the MGI program is putting more attention to the genome level with a focus on the advances in high throughput experimentation to generate very efficiently the raw data that would support rapid expansion of these CalFAD type databases. And the analogy I would cite is the Human Genome Initiative was really enabled by developing those experimental protocols that made the actual measurement of the genome very cost effective. And I think that's really where we've shown what the CalFAD approach can do. The opportunity is broadening its capability.